Hello students, I hope all of you are good and you are studying and also taking care of yourself and your family members. Here is the next lecture on the numerical solution of ordinary differential equations. On Monday's Zoom conference session, we have started this topic, numerical solution of ordinary differential equation, which is the just next topic after numerical integration, and we have seen this slide there also. Okay, I am just keeping this slide for continuity. In that class, in that session, video conferencing session on Zoom, we have seen why it is important to study numerical solution of ordinary differential equations. We have seen there what is the model problem that we are going to study here, or what is the model problem that we are going to face here. That was initial value problem, that is dy by dx is equals to function of two variables x and y subject to some initial condition y at x naught is equals to y naught. Okay, so our purpose here in the course of numerical and statistical methods is to solve ordinary differential equations by using several numerical techniques. These numerical techniques falls mainly under two categories. What is the first category? The first category is we find a series for y in terms of powers of x. Right? Here we have seen Picard's method and Taylor's method. I hope you are thorough with these two methods. I hope you know what is happening in these two methods because you have submitted the assignment related to the same. Okay, right. In the second category of methods of solving numericals or numerically solving ordinary differential equations, we have these methods where the set of tabulated values of x and y we have to find out, or we will be given with some values and we have to find the subsequent values giving some using some formula. These types include Euler's method, modified Euler's method, Runge-Kutta method, Adams-Bashforth method, Milne's method, etc. Out of which in the last video conferencing session on Zoom, we have seen Euler's method and modified Euler's method. We have seen how these two methods work. We have seen what is the difference between Euler's method and modified Euler's method, and also one example each of both the methods. In today's class, the main purpose is to study the next method in the list, which is Runge-Kutta method. Alright, so let us move towards Runge-Kutta method. Right, Runge-Kutta method is also sometimes referred as fourth order Runge-Kutta method. This method is most commonly used to solve ODEs and is referred to as classical Runge-Kutta method or Runge-Kutta method only. Runge-Kutta method, the abbreviation for that is RK method. Sometimes people use RK method or RK4 they will say because it is of fourth order. RK method is developed around 1900 by German mathematicians Karl Runge and Wilhelm Kutta. Euler's method is less efficient in practical problems since it requires h to be small for obtaining reasonable accuracy. This problem we have seen. This is the shortcoming of the Euler's problem. I have discussed it, this thing there also in that Zoom conferencing session. Right? For that we have tackled Euler's method using modified Euler's method. What we do in Euler's method? We approximate the curve, the solution curve, by the tangent at the subinterval points. The slope of the tangent at subinterval points. Okay, but that is not sufficient to gain the required accuracy with some large value of h. So we go for modified Euler's method where we take the average of the slopes of two tangents there. Okay, coming back to the third point, back to the method, Runge-Kutta method. The Runge-Kutta methods are designed to give greater accuracy and they possess the advantage of requiring only the function values at some selected points of the subinterval. So it is efficient in a way that it is more accurate than those methods. Why? Because it requires only one function values at some selected points of the subintervals. We will see it in detail. Okay, these are some highlight points. Here the weighted average of the slopes is taken. Right? Here the weighted average of the slopes is taken. Unlike in the case of Euler's method where we take only one slope. Here what we are going to do? We are going to take four slopes and we are going to take their average. Not just average. We are going to take their weighted average. So let us see how this fourth order Runge-Kutta method looks mathematically in the next slide. We will consider the initial value problem. Dy by dx is equals to function of x comma y, where y at x naught is equals to y naught. This is the standard format of the problem. This is our model problem as discussed earlier also. Here y is unknown function of x which we would like to approximate. We want y in terms of x. Okay, right. For finding the increment k of y corresponding to an increment h of x by Runge-Kutta method, that is our purpose, we have the formula. We have the following formula, which we are not going to prove this formula over here because it is out of our syllabus. Interested readers can go through SS Sastri book, where the not exactly derivation they have given, but they have given some more details regarding that. Derivation is also not there in Shastri book also, but yes, you can refer that book for further clarifications. Okay, then what is the formula? Formula is yn plus 1, which is the next approximation for y. Next approximation for y, yn plus 1 is equals to yn, which is the current approximation, plus some k, where n is running from 0, 1, 2, 3 and so on. Where, what is that k then? That k is equals to 1 by 6 into k1 plus 2k2 plus 2k3 plus k4. And what is that? It is the weighted average of k1, k2, k3, k4, and they are calculated successively as, basically they are weighted averages of the slopes, because k1, k2, k3 and k4 are the slopes. We have seen slopes in Euler's method, we have seen slopes in modified Euler's method. Similarly, this k1 to k4 are the slopes here in Runge-Kutta method. There should be some formulas for them. So k1 is given by h, which is the step size in x direction, h into f of xn by n. You just put the value of n. Suppose it is 0, so it will be f at x naught y naught. It is 1, so f at x1 by 1, and so on. K2 is h into f of xn plus h by 2, comma yn plus k1 by 2. This k1 which I am talking about, this k1 is nothing but, this k1 is nothing but, his k1 is calculated just from here, just from the above step. Okay, so and k3 is equals to, pattern is same for k2 and k3. K3 is equals to h into f of xn plus h by 2, yn plus k2 by 2. This k2 is just now obtained from above. Right, for k4 we have the formula h into f of xn plus h, yn plus k3. Here h by 2 is not there. H by 2, nothing is there. By 2 term is not here. Alright, fine. So, we will discuss the examples based on Runge-Kutta methods in the next video lecture. Stay tuned.